Hello, and welcome to the presentation on electrified drivelines for medium-duty trucks. My name is Bogdan Havrisciuc, and I work for McLaren Engineering in the Electrified Axle Group. Today we're going to look at the energy usage for three different electric driveline architectures for medium-duty trucks and compare how the energy usage is among these three architectures. McLaren Engineering is the product design branch of Linamar Corporation. We have the capability to design, build, validate, and manufacture our engineered products, and we have offices in North America, Germany, and China. McLaren Engineering has a broad experience in engines and driveline systems, and we're leveraging all that expertise and knowledge when designing our electrification drivelines. For medium-duty trucks, in this case represented by a delivery truck, there are basically three types of electrified driveline architectures: the direct drive, the central drive, and the eaxle. For the direct drive system, we have a larger high torque motor coupled to the prop shaft, coupled to the axle, which sends the torque out to the wheels. For the central drive system, we have a smaller high-speed motor coupled to a one-stage gearbox, coupled to the prop shaft, coupled to the axle, which sends out the torque to the wheels. And for the e-axle, we have the same smaller high-speed motor coupled to the two-stage gearbox, which includes the axle tubes, which send the torque out to the wheels. The vehicle model is a modified version of the BEV model in GT Suite version 2020. The components highlighted here in red are the components that are interchangeable between the different driveline architectures: the motor, the gearbox, the prop shaft, and the axle. All of the other components remain the same for all of the different architectures. This slide shows all of the common vehicle parameters: the vehicle, the driver's settings, the battery state of charge, and the battery controller remains the same for all of the runs for the different drivelines. The exchangeable driveline components are the electric motor, the gearbox, the prop shaft, and the axle. For the e-motor, we have the high-speed motor capable of reaching 9,000 RPM, and the high-torque motor reaches 2150 Newton meters. For the gearboxes, on the central drive, we have a single-stage gearbox, and for the e-axle, we have a two-stage gearbox. The prop shaft and the axle are the same for both the central drive and the direct drive, and these could possibly be carryovers from a traditional driveline system where you have an ICE engine. In summary, if we connect a high torque motor to a prop shaft to an axle, this is the direct drive system with high torque motor number 2. Now I'm naming this one high torque motor number 2 because I'm using two different high torque motors to compare the difference in electrical usage given the same hardware. What will be the difference between the two different motors? So high torque motor number 1 connected to the same hardware, same mechanical system, will be direct drive system with high torque motor number 1. The high speed motor connected to a single stage gearbox connected through the prop shaft to the axle is a central drive system, and the same high-speed motor connected to a two-stage gearbox will be the e-axle with the high-speed motor. You can notice that the overall ratio between the central drive and the e-axle is the same, so that we can compare, given the same high-speed motor and the same ratio, we can compare what the mechanical losses are between these two systems given the same motor and the same vehicle. The driveline components were selected to meet this vehicle application. On this slide, we have an example of the central drive because it has all of the components that we find in all of the 3 different architectures. The electric motor was selected based on the torque capability, and the torque curves and efficiency maps were provided by the manufacturer, and we got it either directly from the manufacturer or through other sources. The gearbox was modeled in Romex based on our best practices. The prop shaft, we assumed universal joints on each side of the prop shaft, and the efficiency is based on studies that have been published online. The conventional axle was modeled in Romex and was correlated with efficiency results that we have for a dyno test of a benchmark product. The drive cycles used in this simulation are shown on this slide. The HDU-DDS is considered our city driving, and you can see the time versus speed trace on this graph. We do have some stop and go and a very short period of higher speeds. The HHDDT cycle, just the highway portion, is spending more time at a higher speed. And the NREL Class 6 EV cycle is a custom drive cycle based on some recorded data from similar sized trucks. You can find more information about these drive cycles under these links. Looking at the results, we have here the energy consumed by the vehicle, which includes the energy used for acceleration, to overcome the road loads, and to overcome the aerodynamic drag. The electrical losses are including only the electric motor electrical losses, and the mechanical losses include all of the mechanical components inside of the driveline, from the bearings, gears, churning losses, the universal joints for the prop shafts, all of the mechanical components from the motor up to the wheel end bearings are included in this summation of the mechanical losses. This diagram shows a central drive system on a delivery truck because it contains all of the driveline components that we have in all of the different architectures. Now I split the diagram in order to line up the components to the graphs here, and we see that the energy consumed by the vehicle will be the same regardless of what driveline we use to propel the vehicle. Whether you're using a Flintstone style system where you push it by your feet, or use an traditional ICE engine or a electrified driveline, the amount of energy needed to push this vehicle on a drive cycle using the same speed trace will be the same for every single driveline architecture. The losses from the electrical motor will change depending on how efficient your motor is. The high-speed motor on the e-axle and the central drive have some of the lowest losses, and given that it has the same ratio and same vehicle, the motor is seeing the same torques and speeds, so it has very similar or exactly the same power losses for the motor. We see here that the high torque motor, number 1 and number 2, have higher losses, and these are 2 different motors, so they have 2 different efficiencies and 2 different power losses. For the mechanical losses here, we have the e-axle, one of the lowest losses because there's only a 2-stage gearbox in the system, while the central drive has one of the highest losses because it has the single-stage gearbox, the prop shaft, the conventional axle, And so there's a lot of mechanical components in this system. The direct drive only has the prop shaft and the conventional axle, and so the energy losses are somewhere in the middle. You can see that regardless of what motor we use for the direct drive, the mechanical losses are both the same. So we're using the same vehicle, using the same mechanical components, but different motors. The mechanical components have very similar losses. The slight difference here is because if the motor cannot achieve a certain speed in the same time trace as the drive cycle is asking for, there may be a lower torque or a slight delay in speed due to the driver aggressiveness. If we take the 3 different drive cycles and we average out the results from these 3 different drive cycles, we can see what the overall energy loss for the different components are. So if we average out all the blue lines here, we can get a energy consumed average by the vehicle. Same thing for the electrical losses. We would have an average electrical losses for each of the driveline architectures, and same thing for the mechanical losses. So here we have the average of the vehicle consumption, the average of the electrical losses, and the average of the mechanical losses based on all the different drive cycles. If we take the average vehicle consumption, added to the average electrical losses, added to the average mechanical losses for each of these driveline architectures, and we stack it all together, we have this graph here showing what the vehicle plus electrical plus mechanical losses, and then the total energy consumed for the different architectures. For the eaxle, we have 0.621 kilowatt hour per kilometer. The central drive is 0.666 kilowatt hours per kilometer, and in the best case, the direct drive is 0.719 kilowatt hour per kilometer. One interesting find here is that the central drive, the mechanical losses are higher than the electrical losses. So when it comes time for optimizing the system, maybe optimizing the mechanical components will give you a better result than optimizing the electrical components. Whereas for the eaxle and the direct drive, your electric motor is a higher energy consumer than your mechanical losses. So optimizing your electrical motor will probably give you more benefit than trying to squeeze out the optimization from the mechanical losses. When we look at the blue portion here, this is the energy that you're actually using, the energy used to propel the vehicle. So this is your energy out of the system. And then the total here is the energy going into the system. So it takes this much energy to produce this much energy. So if we take the energy out divided by the energy in, we can use that as a efficiency calculation. And so on this graph here, I'm showing the efficiency split up again by the different drive cycles based on the total energy coming out of the system divided by the energy going into the system. For the highway, we have 88% for the eaxle, and in the best case for the direct drive, we have 76% for the direct drive using the high torque motor number 1. You can see for the other drive cycles how the efficiency compares. So, what does this mean for a truck on the road? If you are designing your system with a 200 kilowatt hour battery, the range for the direct drive is 264 kilometers. On the same battery size, with an eaxle, you have a range of 322 kilometers. That's more range given the same size battery by only choosing a different driveline. Or you can design your vehicle for a 300-kilometer range, and in this case, for a direct drive, you'll have to get a 228 kilowatt hour battery. Or with an e-axle, you can get a 186 kilowatt hour battery. So for the same range, you can get a smaller battery if you go with an e-axle system. In summary, we looked at the energy usage of 3 different electrified driveline architectures, and the results are shown in this graph. When choosing the right architecture, efficiency does play a big role, as we've seen when selecting the different architectures. You have different vehicle ranges, or you can select different battery sizes depending on what your targets are for the vehicle. But also other factors are involved here. I briefly mentioned during the presentation that the high torque motor is a lot larger compared to the high speed motor, and so that will play a role in the cost and packaging of the system, but also that the direct drive system and the central drive system may have a potential benefit by carrying over the conventional axle and the prop shaft from a conventional drive architecture. Thank you very much for joining this session, and I hope you have a great day.